In our previous video, we saw the geometric modeling. Now let us move on to finite element meshing, under which we have overview of meshing, basic concepts and definitions, creating finite element model, and checking the finite element model. Overview of meshing. Finite element modeling is central to the ability to perform an engineering analysis of a model using a computer. One of the core strengths of Patran is its ability to help you create a finite element model either from an existing geometric model or through direct finite element operation. Patran provides the following capabilities for finite element modeling. Mesh seeding tools to control specific mesh densities in specific areas of your geometry. Several highly automated techniques for mesh generation. Equivalencing capabilities for joining meshes in adjacent regions. Tools to verify the quality and accuracy of the finite element model. And finally, capabilities for direct input and editing of finite element data. Basic concepts and definition. Following are several topics that include basic concepts and definition related to finite element application. Finite element types. The table here describes the element topology supported by Patran. The column in the table provides the following information. The left-hand column lists 7 element shapes and illustrates each with a common node configuration. The structural uses column describes typical usage conditions for the element shapes. For example, use bar-shaped element if you plan to define the element properties as bar, springs, or cap elements. The mesh support column indicates how mesh or node configuration combinations are supported for each element shape. The complete description of the Patran element library, including numbering conventions and parametric coordinates, are available here. The next one is mesh generation techniques. There are 4 basic mesh generation techniques available in Patran: ISO mesh, paver mesh, auto-tech mesh, and 2-1-2D meshing. This session describes each meshing techniques. ISO mesh. This approach creates element within a regularly shaped region for geometry via simple subdivision. Some key features of the ISO mesh approach are: it requires regular region of surface or solid geometry. Surface regions must have 3 to 4 sides, while solid regions may have 5 to 6 sides. By default, it creates a consistent number of elements in each direction based on a parameter known as global edge length. Element density and spacing can be controlled via the use of mesh seeds, which can also be used to create a different element density on opposing edges or faces of a region. It can create quad or tri-element on surface regions and brick elements in solid regions. For so-called degenerate regions such as triangular surface or wedge-shaped solids where one edge or face is collapsed, appropriate degenerate tri or wedge elements are created at the degenerate point or edge. It is only an approach that automatically meshes a geometric region with brick element. Paver. The paver is an automated surface meshing technique that you use with any arbitrary surface region, including trimmed surface, composite surface, and irregular surface region. Unlike the isomesh approach, the paver technique creates a mesh by first subdividing the surface boundaries into mesh points and then operates on these boundaries to construct interior elements. Some of the key features are: this approach is valid for surface meshes only. It can be used to create quad or tri-element meshes. Quad meshes can contain some triangles but to the nature of approach. Either mesh seeds or the global edge length parameter on its meshing form are used to control element density. The paver method accommodates associated geometry such as curve lying on the surface, which has been associated with that surface using the associate curve surface option of the geometry application form. If such a curve has mesh seeds assigned to it, the paver ensures that the mesh passes through these mesh seeds point. Adjacent regions can be meshed with either the paver or isomesh approach. The mesh density along a common edge becomes a default mesh density for the edge of the adjacent region. Hybrid mesher. The hybrid mesher is a surface mesher that is used internally by TET meshers. It can be used for quad dominant mesh on any surface. The hybrid mesher recognizes mesh seeds and hard points, and its curvature check automatically refines mesh along highly curved edges. The mesh created by it is generally more regular or well ordered than paver, but not as regular as isomesh. Therefore, it is preferable to paver for some geometries and provide an alternative when the paver meshes provides a poor or unacceptable mesh. Some of the limitations of hybrid meshes are: it does not recognize hard curves, it generates more trias than paver, it generally generates poor element meshes on probably geometry, and it is restricted by surface boundaries, that is, each surface is meshed independently and not collectively. Auto-TET mesh. The auto-TET mesh approach is a highly automated technique for meshing arbitrary solid regions of geometry. It creates mesh of tetrahedral four-noded solid element for any closed solid, including boundary representation solid as well as regular solid regions. Some of the key features are: this approach meshes complex solid regions with little user input. TET meshing is a valid technique for meshing boundary region solids, such as solid models imported from most CAD systems. Curvature-based meshing creates high-quality meshes in curvature region. You can specify the density of the mesh in curved region relative to the global element size. Proximity-based meshing produces high-quality meshing through the thickness of thin-walled sections. 1x2D meshing. A planar 2D mesh can also be transformed to produce a 3D mesh of solid elements using sweep and extrude option. The direction and element density in the sweep or extrude element can be specified with this 2D and 3D transformation approach. This technique produces the element that maintain no associative with any parent geometry. This prevents subsequent loads, boundary condition, and properties for being assigned via geometric entities of these elements. Mesh density. To generate a mesh density, Patran must know the size of the element to use for each of the geometric region. Moreover, you may wish to adjust the number of elements upward or downward for a specific area for the model. There are several tools available in Patran for controlling the mesh size density, including mesh seeds, mesh density of adjacent region. These tools combine to allow rapid meshing of geometric model while providing a high degree of control over the nature of your finite element mesh. When you create mesh in Patran, the mesh density along each edge of the region is chosen according to the following order of precedence: mesh seed, mesh density of adjacent region, and global edge length parameters. Mesh seeds. Mesh seeds are a point explicitly defined as an edge of the model to specify where node locations will be along the edges. These seeds can be uniform or vary linearly towards either end, both ends, or center of the edges. You can even specify the specific individual locations for mesh seeds along an edge. Adjacent meshes. When we create a mesh in geometric region, the mesh density created along an edge will normally be used in the meshing of the adjacent region sharing the edge. In addition, Patran uses the concept of mesh paths to guide the subdivision of geometry region when using an isomesh approach. The figure shown here displays the path of the specified mesh density and how they affect the meshing of overall model. Global edge length. Each variation of the create or mesh form contains a parameter called global edge length that defines the proximate length of each element edge. Parameter uses this parameter to subdivide each boundary edge of your model into an integer number of elements, yielding elements closest to this edge value. Using the relationship Number of element is equals to longest geometry edge length divided by the global edge length. Equivalencing. Many geometry models in Patran consist of multiple regions sharing common boundaries. Finite element meshing in Patran is always performed one region at a time, even when multiple geometric regions are selected in meshing form. The element of one region are not connected to the element of the other region and would not share the behavior across the nodes. Equivalence must be explicitly formed by you prior to analysis. Failure to equivalence generally produces invalid analysis result. For example, unconnected regions which are free to fly off into space in a structural analysis. Pattern does not automatically inform you that the region have not been equalized prior to an analysis. If two or more nodes are within this tolerance, they are combined as one node containing the lowest number of node number. The following figure shows the equivalencing process. You have the option of equivalencing all nodes in a region or just those nodes corresponding to a specific group or list. Once the request nodes are equivalenced, all preference to the original higher numbered nodes are automatically changed with pattern to reflect the new equivalence number nodes. The equivalencing option allows you to select nodes to exclude from equivalencing. This is useful for cases where there are coincide nodes that you wish to keep physically separate. In addition, the value and measurement techniques for the equivalencing tolerance value can be set using the equivalence action. Optimizing. No matter how finite the element is created, either by mesh or by direct finite element modeling, there is one short, painless operation that can speed up the analysis substantially. This operation is known as optimization, simply renumbering your nodes or elements to decrease the number of runtime of the problem. Other solvers are based on a similar criteria of wavefront based on the number of active columns in the row. In analysis, terms from each finite element combine to form a symmetric matrix that is sparse containing many zero terms as part of solving this matrix equation by essentially inverting the matrix many finite. Element solvers have a solution time that varies with the bandwidth of the matrix. The bandwidth is the maximum width of the non-zero terms from the matrix diagonal. Finite element application form. The finite element application form provides numerous action, option, and type combination that create, modify, and qualify the finite element model facilities and valid analysis result. To use the finite element form, follow the steps given below on the screen. Action. The action creates, modifies, and qualifies all the mesh-related objects. The table that follows describes the action shown of the finite element application. Please pause the video and have a glance at it. Objects. The object are your mesh-related entities. These include items such as mesh, individual nodes, and elements. The table that follows describes the objects that you may choose on the finite element application form. Please pause the video and take a look at it. Element shape test. Aspect measures the maximum dimension ratio of opposite edges, faces, or principal directions in surface or solid elements. For example, in a quad element, the aspect ratio represents the ratio of length to width. Normally, finite element provides more accurate answers when the aspect ratio is closest to 0. Warp measures the degree to which a quad element corners point are out of plane from the centroidal plane of element. Skew measures the angular deviation from a rectangular shape in surface element. Taper measures the geometric deviation from a rectangular shape in a quad element. Edge angle measures the maximum deviation angle between the adjacent faces of the solid element. Face warp, face skew, face taper measures warp, skew, and taper as described above for faces of a solid element. Twist measures the maximum twist between opposing solid element faces in edge and hex element. Other element tests. Boundary tests for free element edges with no adjacent connect elements. This is an important test to check for inequivalence portion of your model. Duplicates detect multiple elements connected to the same nodes. For shell element, normal check for consistent normal between adjacent element. Jacobian ratio, Jacobian zero tests based on the maximum variation and minimum value of the Jacobian determinants of each element respectively. IDs color code the element based on the ID number. This is useful test for visual verification of element number ranges and order of modeling. We are done with this session. Now let us move on to material modeling in the next session.